Welcome to this lesson on linear algebra, and we'll put that kind of as a quote statement here on the GMAT, because the algebra here is really tailored specifically to what you're going to be doing on the GMAT to address problem solving and data sufficiency questions in the quantitative section of the exam. So let's begin just by talking about how we're going to define, and again, that's kind of in quotes, GMAT linear algebra. So by and large, just definitionally, linear algebra can be represented as a line on the coordinate plane. We'll talk about some things that aren't necessarily lines here in a moment, but that is the technical definition of linear algebra. It's a line. And for linear algebra, there's a single possible value for any variable in an equation at one time. Now, a variable is just an unknown that can be different values, pending values of other variables and or constants that are presented in the equation. Now, a constant is an unknown value that has a single possible constant value. So they're going to tell you that it's constant. You might have to solve for it, but then it stays at that numeric value for the duration of the problem. So a sample linear equation is something like this: 4x plus 3y equals 84. Because if x equals 0, then 3y has to be 28. If y is equal to 4, then we're looking at 4x is equal to 72, and x has to be equal to 18. So just a different couple of things that could be the answers, but there's just one at a time pending the value of the other variable. So the implications of all of this. First, always attempt your technical algebra first for problem-solving questions. If you can do it, it's probably fastest. But remember, abandon that approach as soon as it ceases to be both apparent and simple to you in the moment. Don't keep going back to the algebra well. It is very much just a fact of life that if you're missing something algebraically, it is exceedingly unforgiving. You won't see what the issue is, and then you'll come back to it in your review and you'll go, oh yeah, it's right there. I just, for whatever reason, forgot to distribute that thing. But in the moment, especially on the exam, if you're stuck algebraically, go to a different tactic. Do not try the algebra again, really, because it's just not going to get better unless you go back and you immediately see the mistake on your one allowed reread recalculate. Now, that said, you do want to rely primarily on algebraic translations for data sufficiencies, especially word problems, because those are oftentimes really just testing your ability to articulate the unknowns from the English. So really do use technical algebra for data sufficiencies. But in both problem solving and data sufficiency, beware of auto solving for unsought individual values, or variables. What that means is if they're asking for 18 divided by x, solve for 18 divided by x. Don't solve for x individually. If they're asking for x plus y, don't solve for x and then solve for y. Go solve for x plus y. There's a reason they're asking for the combination, so you want to be efficient and go solve for the combination rather than wasting time solving for an individual variable just because you're kind of on autopilot. So now let's talk about our broad algebraic order of operations. And again, this is going to go a little bit outside of linear algebra. I understand that. It's just really kind of simplifying things for the purposes of this exam. But first, eliminate fractions or decimals by multiplying your full equation by the least common denominator or a power of 10. Again, it's just a fact of life. Humans calculate integers more easily than decimals or fractions. So eliminate entire fractions, or all the fractions with one common denominator. Eliminate all of your decimals by multiplying by 1 power of 10. You know it's an equivalent equation, just get rid of the fractions or decimals as your first step. Then you want to work to efficiently isolate for your sought value or combination of values using the 4 basic functions: addition, subtraction, multiplication, division, following your PEMDAS order. Of course, that's parentheses, exponents, multiplication, division, addition, subtraction, with multiplication and division at the same level and addition and subtraction at the same level. And if you are deciding which order to do those in, just go left to right if you've got an ordering question regarding multiplication versus division or addition versus subtraction. Last, you want to eliminate exponents or radicals by appropriately raising or rooting the full equation. Now, I know this is basically where I'm breaking the whole idea of this being linear algebra. I know, but for the purposes of this exam, it might be easier to just do things in kind of a linear algebra solving approach as opposed to making it into a quadratic. So there is another lesson on quadratics. We'll talk about factoring, distributing, all of those things. But if you're trying to just solve it directly, and you can, just make sure you do the exponent last, because if you do it earlier, you're going to get really, really convoluted. Just make sure that's the last step, unless you're doing it quadratically, in which case you've got a different approach entirely. So we've got an example. 1/4 times the quantity 2x squared plus 8 is equal to 34. So just going to multiply the full equation first by 4 to eliminate the fraction entirely. We now have 2x squared plus 8 is equal to 136, which is probably most easily arrived at by doing 30 times 4, which is going to be 120, plus 4 times 4, which is 16, and of course 120 plus 16 is 136. Then subtract 8 from each side to leave yourself with 2x squared is equal to 128. Divide by 2 the entire equation, so then you've got x squared is equal to 64. Square root the full equation to find that x is equal to positive or negative 8. Remember the negative, because if you square root something, you've got both a positive and a negative possible solution, because positive 8 times positive 8, obviously 64, but so is negative 8 times negative 8. So now let's talk about systems of equations. So these are used to solve for an individual variable or combination of variables when you have multiple equations. And generally the rule is this: you can solve for the exact individual variables if the number of equations is equal to the number of provided variables. Just make sure that you've got unique equations, not equivalent equations, because if you've got 2x plus y is equal to 6 and 4x plus 2y is equal to 12, you really just have the same equation. You also can possibly solve for proportions even if the number of provided variables is greater than the number of provided equations. So it is possible to solve for a proportional relationship without the same number of equations as variables. Just another thing that the exam may like to exploit. So some strategic implications here. First, you want to always articulate your information consistently with the fewest number of possible variables. So that means, like, if we're talking about, say, something that's happening during the months of the year for X months, one of my variables will be X months, one of my variables will be the 12 minus X months that aren't the thing that's happening. Don't assign X and Y months, because you really know that the leftover months is just 12 minus X. Then recognize that substitution of your variables is generally the long way to solving. Not saying that you won't ever substitute, and sometimes it's helpful, especially on data sufficiencies. But generally, if you want to solve for an exact value, a system of equations is the more efficient path. And so instead of trying to substitute and taking that long route, instead seek savvy ways of stacking your equations to eliminate a full variable by finding a common multiple and adding or subtracting those full equations to eliminate that variable at the end, the one that you're not solving for. So let's go ahead and see how that works in practice. First, you want to stack your equations vertically, aligning the variables. Then you want to multiply to find a common multiple of your not sought variable or variables, because I want to get rid of the ones that I'm not looking for, and I don't want to solve for the ones that I'm not looking for. So go find the common multiple of the things you're not looking for and leave behind only what you are. Then, as your last step, you want to add or subtract your equations to eliminate all your variables except for the sought variable and solve for that sought variable following the order of operations we talked about earlier. So we've got an example. What is the value of y if 5x plus y is equal to 45 and 2x minus 6 is equal to 2y? So we just stack them up. 5x plus y is equal to 45. 2x minus 6 is equal to 2y. And then we're going to multiply the top equation by 2, bottom equation by 5. That produces 10x plus 2y is equal to 90, and 10x minus 30 is equal to 10y. So you can see we've got the same number of x's in our two equations. Then we'll subtract those equations to eliminate that x variable. So 10x minus 10x, no more x's. 2y minus 30 becomes addition. So we've got 2y plus 30 is equal to 90, now minus 10y. So then we just have to solve for y. We'd add 10y to each side, subtract 30 from each side. We'd get 12y is equal to 60. Divide by 12, and we discover that y is equal to 5. Probably in the most efficient manner. Now, the other thing you can do with our system of equations is that you can potentially solve for a proportional value with a linear system. Now, first you want to articulate your information algebraically. In this case, we're going to use a word problem in a moment to kind of illustrate that. Then you want to work to isolate for the sought value in terms of the other variables in the most, again, efficient manner. So we've got our example. It's a little bit long-winded, so bear with me, but we've got James is invested in 3 funds, X, Y, and Z. If 10% of the total he invested in X is equivalent to 30% of the amount he invested in Y, and the amount he invested in Z is half what he invested in X, what fraction of his total investment is in fund Z? There's a lot happening here, unequivocally. And if you find yourself entirely lost in the word problem, you might want to consider alternative tactics. So there aren't answer choices listed here, but try the algebra first, because if you can do this technically, it really doesn't take that long. So step 1 is articulating the information algebraically. We know 0.1 x is 10% of x. 0.3, or 10% of the total is in x. So we know that, 10% of the total he invested in x. So 0.1x is equivalent to 30% of what he invested in y. So 0.1x is equal to 0.3y. So again, the English can get convoluted if you aren't careful. So 0.1x is equal to 0.3y. Then we know that the amount he invested in z is half what he invested in x, so that's 1/2 x is equal to z. Then our total is just x plus y plus z. And I don't want to think about my total as a total. I'm just saying it's x plus y plus z, because those are the 3 funds. So then we need to set these totals in terms of x and z only. So we can see that our x is just x. Our y is going to be, well, we eliminate those decimals. We know that x is now equal to just 3y. So y is equal to 1/3 x. So there's our 1/3 x. Then we just have to add the half x, which is what z is in terms of x. And that's equal to x plus y plus z, but this time we leave the z, because we know that x plus 1/3 x plus z is equal to this same thing, only in terms of x. So then we multiply by 6 to eliminate all of our fractions. So now we have 6x plus 2x plus 3x on the left-hand side is equal to 6x plus 2x plus 6z on the right-hand side. So we've got 11x is equal to 8x plus 6z. Now we have to convert our 6z back into an x to figure out what fraction that 6z is out of the 11x that's now known as our total. So 6z is equal to 6 times 1/2 x. Here's where substitution was probably necessary. So 6z is just equal to 3x. And finally, we can just list out that value of 6z in terms of 3x out of the 11x total to determine that the z investment is 3/11ths of the total investment. So that's one of the more advanced things that you can do with linear algebra. Let's go on over to the whiteboard and take a look at a sample problem solving and a sample data sufficiency question to see how we can further apply these concepts to the quantitative section of the exam. So let's take a look at this sample word problem. As we always do, let's set up our scratch pad first. So we've got A, B, C, D, E, and some relatively simple numbers, and numbers with a relatively big range as well. So I definitely would encourage you to write these out, because there's the possibility of a logical estimation opportunity if there's this big of a split in our answers. And you can also shorthand your answers when you see thousands with just 110K, as I'm doing there, or 185K as we see here, 220K for choice E. So if we skip to the end, we see what we're looking for, and we're being asked for the variable cost per widget. So cost per W at SC, and we'll just call it for Sasquatch Corporation. We'll know what that abbreviation means for the next couple of minutes that it matters. So then we see at the beginning Sasquatch Corporation's total monthly expenses, so our total is equal to a fixed monthly production cost. So we'll just say that's F. And a variable production cost. Okay, so that we'll just call our X, which is the thing we're solving. So plus our X, that is directly proportional to the number of widgets. So we'll just call that number of widgets W. So we've got our equation set up here as total cost is equal to F plus XW. Then we're told if Sasquatch Corporation's total monthly expenses are $405,000, okay, so that's a 405,000, in a month in which it produces 1,000 widgets, oh, okay, so that's equal to F plus 1,000, which is my W, times X. And 515,000, so 515, comma 000 is equal to f plus 1,500 times x. Now we just have to solve for x. And since we have two equations and now only two variables, since they've given us the values for the w's in these different months, we can just stack and solve. So we'll put our bigger equation on top to subtract our smaller one and thereby eliminate the entire f variable. So we've got 515,000 is equal to f plus 1,500 times x. And then we've got 405,000 underneath is equal to f plus 1,000 times x. Now, as we set up this equation, you remember at the beginning I said there's probably a logical estimation opportunity. And just looking at these two equations, there's no way I'm going to be multiplying something in the 100,000s times 1,000 to get 515,000 or 405,000. So always look back to your choices to logically eliminate answers, just to make sure that if you get stuck at some point from here on in, you don't pick C, D, or E. These are all way too logically impossibly big. So those are all out. We know we're down to A or B. Now we just have to do the math and eliminate F in order to solve for it exactly. So we subtract out our two equations from, well, the bottom one from the top. And 515 minus 405 is just going to be 110, and we bring down the 1,000. We subtract F from F, so the F's are gone. And then 1,500x minus 1,000x is just 500x. So then we can do the long division, honestly. It's not that difficult. It's really just bad marketing on the part of division. But we've got 500 into 110,000. So 500 goes into 1,100 two times. Subtract out the 1,000. So we bring down 1,000. So 500 goes into 1,000 two times, and then we just have zeros. So there's my 220, and that is the variable cost per widget at Sasquatch Corporation. And again, technical approach is great, but if you get stuck, look for that logical estimation opportunity too. So now let's scroll on down and take a look at a data sufficiency example. So we've got this one, not much to go on. We're just being asked, is y equal to 0? And of course, this is a yes-no data sufficiency, so we'll box that off so we don't lose sight of what we're being asked for. But we want to consider what we need, and we need is going to be our y equation. So one equation for y. And again, always do put something in the need. Don't give in to that urge to just skip over it. It's going to focus you on what you need to solve for. So condition 1 says that 5x plus y is equal to 15. Well, right now I've got two variables in one equation, so I can't solve. So that's not sufficient, and our options, of course, are B, C, or E. Now, if you're not confident in the algebraic manipulation here and the algebraic evaluation of sufficiency, you can just plug in y is equal to 0 and go, well, then x would be 3. Or plug in y as 1, or I guess not 1. Actually, it can be anything because there's no restriction on there being a integer here. So that's okay. But then condition 2, we've got 2x minus 6 is equal to 2y. So again, two equations, only one variable, that's not going to be enough. Now, the real catch here is that when I see that I've got two unique equations and two variables, I know that I can solve and I don't need to solve for y at this point. Because whether x or y is or isn't 0, this is sufficient at this point. So ideally, we'd like to go ahead and select C immediately. But just to prove it out, we can always multiply by 2 and 5 respectively to get rid of all of our x variables. So that would produce a top equation of 10x plus 2y is equal to 30, and a bottom equation of 10x minus 30 is equal to 10y. So then we subtract out right there. We've got the 10x's cancel. We've got 2y plus 30 is equal to 30 plus 10y. We subtract 30 from each side. And we subtract 2y from each side. And we discover that indeed 0 is equal to y. So again, don't need to do this last step. In fact, I probably don't want to. But just to illustrate how we'd solve using this tactic technically, so that you can apply the same sort of concept to your practice quantitative problems, data sufficiencies, and problem solving as you practice more questions for your GMAT prep.